Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're analyzing a Google Cloud exam question about optimizing Cloud VPN for both throughput and redundancy. This is a critical topic for anyone designing hybrid connectivity solutions. The scenario states that hybrid connectivity is already established between GCP and on-premises using Cloud VPN, but they need to increase throughput. The question asks which configuration provides the highest throughput and redundancy. This question tests your understanding of two key Cloud VPN concepts: how VPN gateways and tunnels work together, and the throughput limitations of each component. Many people get confused about whether adding more gateways or more tunnels provides better performance. The key insight is understanding that each Cloud VPN tunnel has a maximum throughput of 3 gigabits per second, and each Cloud VPN gateway can support multiple tunnels. Let's explore how different configurations affect both throughput and redundancy. Understanding Cloud VPN components. Before we analyze the options, let's understand the building blocks of Cloud VPN and their limitations. A Cloud VPN gateway is a regional resource that serves as the GCP side endpoint for your VPN connections. Think of it as a virtual appliance that Google manages for you. Each gateway gets external IP addresses that your on-premises VPN devices connect to. A VPN tunnel is the actual encrypted connection between a Cloud VPN gateway and your on-premises VPN device. Each tunnel is a separate IPsec connection with its own encryption keys and traffic flow. This is where the actual data travels. Here's the crucial performance fact. Each VPN tunnel supports a maximum throughput of 3 gigabits per second. This is a hard limit per tunnel, regardless of your actual internet bandwidth or the gateway it's attached to. If you need more than 3 gigabits per second, you must use multiple tunnels. For redundancy, you need to think about both gateway level and tunnel level failures. If a gateway fails, all its tunnels fail. If a tunnel fails but the gateway is healthy, other tunnels on that gateway continue working. This distinction is important for designing highly available solutions. Cloud VPN supports ECMP, or Equal Cost Multipath, routing, which means if you have multiple tunnels to the same destination, traffic is automatically load balanced across all healthy tunnels. This is how you achieve both higher throughput and redundancy. Let's analyze each configuration option to understand their throughput and redundancy characteristics. Option 1 proposes 2 Cloud VPN gateways with 1 tunnel each. This gives you a total of 2 tunnels, providing 6 gigabits per second of maximum throughput. For redundancy, if one gateway fails, you lose 50% of your capacity but still maintain connectivity. This provides good gateway-level redundancy, but it lacks tunnel-level redundancy on each gateway. Option 2 is a single Cloud VPN gateway with 3 tunnels. This provides 3 tunnels on one gateway, giving you 9 gigabits per second of maximum throughput. However, this creates a single point of failure at the gateway level. If the gateway fails, you lose all connectivity. This maximizes throughput but has poor redundancy. Option 3 is our winner. It uses 2 Cloud VPN gateways with 2 tunnels each. With a total of 4 tunnels, 2 per gateway, you get 12 gigabits per second of maximum throughput. For redundancy, if one gateway fails, you still have 2 tunnels and 6 gigabits per second of throughput on the other gateway. If a single tunnel fails, you have 3 remaining tunnels. This provides the best combination of throughput and redundancy. Option 4 describes a single Cloud VPN gateway with 2 tunnels each. The wording here is confusing because the word each doesn't make sense with a single gateway. Assuming it means 2 tunnels total on one gateway, this provides 6 gigabits per second of throughput but suffers from the same single point of failure issue as option 2. The pattern is clear. Multiple gateways provide redundancy against gateway failures, while multiple tunnels provide both increased throughput and redundancy against tunnel failures. Option 3 maximizes both dimensions, visualizing traffic flow and failover. Let's visualize how traffic flows in the winning configuration and what happens during failures. In normal operation with 2 gateways and 2 tunnels each, traffic is distributed across all 4 tunnels using ECMP routing. If your on-premises router supports ECMP, each packet can take any of the 4 paths, effectively giving you 12 gigabits per second of throughput. The load balancing happens automatically at the routing level. When a tunnel fails, it is automatically removed from the routing table. This is handled by Cloud Router if you're using dynamic routing, or by your static routes. Traffic seamlessly redistributes across the remaining 3 tunnels. Your throughput drops to 9 gigabits per second, but there's no connectivity loss. The real advantage shows during gateway failures. If Gateway 1 completely fails, for example during maintenance or an outage, you lose its 2 tunnels, but Gateway 2's 2 tunnels continue operating. Your throughput drops to 6 gigabits per second, but again, no connectivity loss. This is why having multiple gateways is crucial for true high availability. Compare this to the single gateway options. If that gateway fails, you lose all connectivity regardless of how many tunnels you had. This creates a complete outage for your hybrid connectivity, which is unacceptable for production workloads. This configuration also provides flexibility for maintenance. You can take down one gateway for updates while maintaining connectivity through the other, then switch and update the second gateway. This enables zero downtime maintenance windows. Implementation best practices. Now let's look at how to implement this configuration correctly for maximum benefit. First, always use HA-VPN instead of classic VPN for new deployments. HA-VPN automatically creates 2 interfaces per gateway and establishes a 99.99% SLA when properly configured. With 2 HA-VPN gateways, each with 2 interfaces, you get 4 tunnels by default, which is exactly our winning configuration. For routing, use Cloud Router with BGP instead of static routes. BGP automatically handles failover and load balancing without manual intervention. Configure your on-premises routers to advertise the same prefixes through all tunnels with equal MED values to enable ECMP. Place your gateways in different zones within the same region for additional redundancy. While VPN gateways are regional resources, specifying different zones provides some protection against zone-level issues. The command would include region as Central 1 and Zone as Central 1A for the first gateway, and Zone as Central 1B for the second. Monitor your setup actively. Use cloud monitoring to track tunnel status, throughput per tunnel, and packet loss. Set up alerts for tunnel failures and high utilization. If you consistently use more than 80% of your total capacity, it's time to add more tunnels. For cost optimization, remember that you pay per tunnel hour. 4 tunnels cost twice as much as 2 tunnels. However, the cost difference is usually negligible compared to the business impact of an outage. The extra redundancy is almost always worth the additional tunnel costs. Thank you for your attendance. Please consider subscribing to the channel.